All right, so let's start. Today we are going to do something that we have seen earlier. All right, so we saw this approximation, depletion approximation being made in Schottky barrier diodes and in PN junction diodes also. And it's a very important assumption which allows us to determine electric field, determine potential, determine capacitance. And therefore, what we'll do is we'll look at this particular assumption, this depletion approximation, in a little bit more detail. Okay. All right. So let's start then. Let me show you first a approximation here. See this particular graph on the left here. So let's say right now we are not talking about depletion approximation. It's just a mathematical graph here. Say there's a function which is constant and then decreases like this here on the right and on the left like this here. The constant part is 0.14. Say micron doesn't matter. Let's say the length of this particular one is same as the length of this particular one. Can we approximate this graph by something of this kind? Does it look like a good approximation? No? Under what conditions do you think I can approximate this by this one here? If I can approximate this graph by this one, under what condition? If this region here is much smaller than this particular region, right? That's what we would tend to think here. Then we can approximate. Then this particular approximation may be true. All right. Okay. So let's see how this is relevant to our depletion approximation. So we've seen earlier that when we have a PN junction, at the junction here, the electrons from the N side have gone over to the P side and recombined, and they've left behind ionized donor atoms here. And similarly, the holes have recombined with electrons, and we are left with the ionized acceptor atoms here. So we have negative charge here and we have a positive charge here. And we expect that as you start from here, this is a neutral region. We expect that the electron density will be, of course, equal to the donor density. But then as you go inside this particular space charge region, electron density reduces. This is what you see here. Electron density is constant and starts reducing. And pretty soon what happens is it doesn't become zero, but it becomes much smaller than the donor concentration here. And therefore, what happens is electron concentration becomes much smaller than donor. And therefore, in this particular region, charge rho, which is nothing but Nd minus N. So the charge then increases here and then practically becomes equal to Nd here, right? Because the electron density has become much smaller than the background charge here, donor density. And something similar happens here. All right. So we expect that the charge density in this particular region here, charge density will be constant and then starts to decay in some manner here and eventually goes to zero here. So that's what we expect in this space charge region here. Throughout our discussion, what we'll do is we'll assume a symmetrical PN junction. Symmetrical in the sense that doping here is the same as doping here. So whatever I'm talking about this region, the same thing holds for this region also. Okay, just for simplicity. All right, so we expect rho to go like that here. The reason being is electron density goes in this particular manner here. All right. Okay, so now the trouble is, as we have seen earlier, rho goes like this here. And this rho is what we have to integrate using Poisson's equation, right? So Poisson's equation tells us del square psi by del x square is minus rho by epsilon s. Rho in general is this one here. Now, if I look at N side, I don't have to bother about Na minus, and I don't even have to bother about P. So I'm left with Nd and minus N. Now, the trouble is that N and both P, they go as exponentially with psi. N goes exponentially with psi. P also goes exponentially with psi. So if I'm looking at the N side of the junction, N side of the junction will be Nd plus minus N, and N is going as e to the power q psi by kt. So my Poisson equation on the right hand side then has a psi here with an exponential here. And that makes now the solution of Poisson equation difficult. It becomes a difficult problem, and therefore analytically is difficult to solve, and numerically of course you can do it, but analytically is difficult to solve. And therefore what we do is we make an approximation that the electron density and the hole density within that space charge region is much smaller than the doping, Nd and Na. And therefore, rho in general becomes then you neglect N and P within the space charge region. And that's why we tend to call it depletion approximation. You're neglecting N and P. And then rho simply becomes equal to QND plus X minus Na minus X here. So if I'm looking at the N side, I only have doping, so it becomes QND. If I'm looking at the P side here, then I have only Na, and then it becomes minus QNA. So that's the approximation that we end up with. All right, assuming N and P is much smaller than Nd and Na here. And based on that, in the last lecture, we had derived expressions for electric field. So right now we are assuming a symmetrical junction, same doping on N and P side. So we had done the derivation last time. So electric field is QES Nd doping here times Xn. And both Xn and Xp are the same. Whatever is the extent of depletion width here, the same is here because of symmetrical junction. And potential and depletion width, which will be nothing but twice Xn. 2 times Xn, depletion width can be derived in this particular form here. So we can determine maximum electric field, we can determine electric field profile, we can determine depletion width. And in the context of metal semiconductor junction, I had shown you that once you have a depletion region, you can define a capacitance per unit area, which is ES by W here, depletion width. So one can get a capacitance also. So just like in a metal semiconductor junction, we had a depletion capacitance, here also we have a depletion capacitance, which is nothing but it's like a parallel plate capacitance, epsilon S by W here. In metal semiconductor junction, if you recall, we had said if I take 1 over Cj square and plot it versus B, it's a straight line. Same thing happens here. If you look at this expression here, if you take 1 over Cj square and plot it, you'll get a straight line here. And if you extrapolate, you can get the built-in voltage of the PN junction. If you take the slope here, you can get the doping here. So these are useful things that one can get from the capacitance measurement here. All right, so this is what we do in depletion approximation. Now, depletion approximation is not just made in PN junction. Of course, it is involved in all the devices which are PN junction. And I'm just showing you a couple of them. Bipolar junction transistor. There's a junction here and there's a junction here. So we make depletion approximations here and here to find out what the depletion widths are here and here. That's a BGT. HBT is also a bipolar transistor, except that the name is heterostructure bipolar transistor, except that the material that you use in emitter semiconductor is different from the semiconductor that you use in the base. And that's why we call it a heterostructure, because 2 different semiconductors are being used here. So it's nothing but a bipolar junction transistor. Thyristor, you have a PN-PN structure here. You have a depletion region here, here, here. JFET, junction field effect transistor, we'll see a little later on towards the end of the PN junction. So this is a transistor, this being source, this being drain here. The current flows from the source to drain, and the current you can alter by applying a voltage to the gate here. As you apply voltage to the gate, there's a depletion region here, so you can control how much of the channel is present by applying a voltage here, and that determines the current here. So anyway, JFET, you can see a PN junction. MOSFET, of course, you can see a PN junction here, N plus P and N plus P here. So you see PN junction and you see depletion approximation being made in a wide variety of devices. Not just that, there are devices without PN junction. For example, Schottky barrier diodes we had seen earlier. We make depletion approximation here. We had seen this also, MESFET, metal semiconductor field effect transistor here. This is a metal semiconductor junction. It is based on the modulation of channel using the gate voltage here. Again, we make depletion approximation to determine what is the current flowing here. Something similar, this is called a high electron mobility transistor, which also has a metal semiconductor junction. That also has a metal semiconductor junction where we make depletion approximation. So you're saying depletion approximation being made in almost all the devices that we use here, very widely used here. And therefore, it's important to understand what the limitations of this particular approximation are. So the issue that we are dealing with then is, we know that rho charge density goes like this here. There is a constant region where the electron density is very small compared to the doping, and therefore is constant. And there is a transition region here, right? And as I said, we'll consider symmetrical junctions, so both sides are the same. And we know that what we are doing is, we are in depletion approximation, we are approximating it by constant charge density up to a certain region and then 0 abruptly. This is because we are taking symmetrical junction. This is half the depletion width here, half here. Okay, so this is the approximation that we are making. So the issue is how good is this approximation? And as some of you said, that, and it's a common belief, the depletion approximation will be good if the transition region that you see here, LT, is much smaller than, let's say, half the depletion width, right? Say I figure out what is the transition region here, LT. And then I know what my depletion width is, right? We are already calculating depletion width. We have expression. And therefore, if this LT is much smaller than W by 2, one may say, well, the transition region is a very small region here. I can sort of neglect it. Okay? So, which means that in order to check my depletion approximation, I have to determine what is the extent of this region here. All right, so we have to do analysis to determine how much is this transition region length here. And then we already have expressions for W, and we'll check. We'll check whether LT is much smaller than W or not. Okay, so let's do that. So what we are doing next is finding out how large is this transition region. We also call it a boundary layer. Boundary layer, that's the layer at the boundary of the space charge region here. So the way we do it is, to find out this extent of this particular region, we start with Poisson's equation, del square psi del x square here. And now in this boundary region here, obviously I can't make depletion approximation. So I have minus q by ES. Actually, it should be minus q by ES nd plus n here, okay, or nd minus n here. So q by ES should go outside. And therefore, we have n also in this particular region here. So I have to look at n in this. All right, so let's see how we can do that. N we know, we are talking about equilibrium right now, okay? N equal to NC e to the power minus EC minus EF by KT. If I have two regions, two points in my semiconductor with at two different points, so N2 by N1 I can write it as, because equilibrium, EF is the same everywhere. So N2 by N1 I can write e to the power EC1 minus EC2 by KT, right? So just from this equation here. We use the concept now that potential is equal to minus EC by Q. Potential is related to conduction band through minus 1 over Q because of the charge here, plus some reference. It doesn't matter what the reference are. We can take Fermi level as a reference. We can take something else as a reference here. So psi is related to EC. So N2 by N1, one can then write it as N2 by N1 is equal to e to the power psi 2 minus psi 1 by KT. The same reference is being used for both, obviously, and therefore EC1 minus EC2 would be nothing but psi 2 minus psi 1 by KT here, right? So that's the ratio of the two electron densities here. Let's come back now to this transition region here. The transition region, remember, was starting from here, somewhere here, and then it builds up, and I'm showing the potential here. Okay, now, so I'm showing the potential variation. So remember, we know that the net potential across the space charge region is built-in voltage, VBI. Now I can take anything as a reference. For example, I could start and say potential here is 0. And then potential at this end would become minus VBI. Or I could have done the following. I could have said potential here is 0. And then the potential here would have been plus VBI. So it doesn't really matter what reference you take. In all of these cases, what is important is what is the drop. Okay. So let me take potential here at the edge here is 0 in the N region. And then as you go into the N, potential becomes negative, and then eventually it reaches VBI here, right? So now if I take N1, the point here somewhere in the neutral region here, so N1 then becomes equal to ND, because we are talking about neutral region, so N1 is equal to ND. Potential here, psi 1 is 0, right? So we'll take N1 equal to ND, and psi 1 is 0, and then potential anywhere inside the device, we'll just take it as psi. So we get this expression here, N equal to ND e to the power psi by KT. N now within this space charge region here. So if, as I said, somewhere here is neutral, psi is 0, and N equal to ND as we expect. As you go further into it, psi is negative. Note, psi is negative, so N starts dropping. N starts dropping, and eventually, because it's an exponential function, N will become very, very small. All right. So this is N here. So let's take this expression for N, put it in a Poisson's equation. So we had del square psi by del x square minus q by ES. Again, it should be ND minus N. we take n equal to nd e to the power psi by kt. We take this one, plug it here. All right. When we do that, then we get this expression: del square psi del x square minus q by es nd plus q by es nd e to the power q psi by kt. All right. So we get this now Poisson's equation. Again, because of the exponential, it's a little bit difficult to handle here. But note that we are interested in this small transition region here, in this boundary layer here. And in this boundary layer, you start from 0, and then you're looking at potential boundary layer if we assume that boundary layer is small and the potential drop is small, then what we can do is we can say, well, e to the power q psi by kt can be approximated by a linear approximation. Because you're starting from 0 and you're looking at a region which is in the neighborhood of 0. Okay, so what we do is we expand e to the power q psi by kt, and we write it as 1 plus q psi by kt. All right, just to get an analytical expression. Okay, we do that and we substitute it here, and then we get del square psi by del x square is psi L square dn, and where dn is what we call as Debye length and is es kt by q square nd. So this is the Poisson's equation that we get after approximating the exponential by a linear expansion. So now if you look at this Poisson's equation, in this region here, in the boundary layer here, if you look at this, it says what? Potential. How does it go with x? Del square psi by del x square equal to psi by L square dn. What does it say? Potential goes exponentially with this one here. And note now, potential is changing exponentially on a length scale of what? This is the length scale, which we call as a Debye length. And how does n change? N changes exponentially with psi. All right. So now, what do you think is the extent of the boundary layer, the transition layer? I'm not going to solve this. This is simple to solve, but what do you think is the extent of the boundary layer here? Potential is changing exponentially with LD, and then electron density is changing exponentially with psi. Or, because exponential is a linear approximation, so it's linearly with psi here. So over what length scale do you think n will become much smaller than nd? LD or couple of 2-3 LDs, right? Okay, 2-3 LDs, because exponential, you know that whenever you have an exponential function, all of you say 3 taus and all that become, right? So now what we are getting is then the following, that this is what is known as the Debye length. We have an expression here. And so what we can say is that the boundary layer here is about, let's say, 3 times the Debye length. The boundary layer is 3 times the Debye length. Okay? And again, how you define the boundary layer depends on how far you want to go. You want to go to 10% point or 1% point or whatever, that there's a bit of subjectivity here. But 3 times LD is a good measure, and I'll show you later on that if when you take 90% to 10%, it does come out to be roughly around that value here. All right, so we know the extent of the transition layer here. This is the transition layer here, and the transition layer will be about 3 times this Debye length here. We know the depletion width here, xn, we have already calculated. Xn is square root 2 es Vbi by qnd. We've already solved Poisson's equation under depletion approximation. We know how much is the depletion width on this side here. And the same is on this side, by the way. Okay, so we know this here. So let's compare the two of them. So what do we do? Well, if you look at this, compare the two of them, you can write xn equal to LDN square root 2 Vbi by kt by q. Both of them depend on nd, both of them depend on es, is the same dependence. So we can compare the two, xn equal to LDN square root 2 Vbi by kt by q. And then let's take some typical values. If I take Vbi of 0.9 volt, Vbi of 0.9 volt, then xn, which is the extent of depletion width here, divided by LD is 8.3, which means that this region here is 8.3 times Debye length. But how much is this region here? 3, right? So what will be the ratio of xn divided by the transition region? It would be 8.3 divided by about 3, right? So if you work out, you find that the boundary layer, this is the boundary layer here, boundary layer here, and the boundary layer here. Boundary layer divided by depletion width is about 38.5%. All right. So we have found out the extent of the boundary layer here, which is 3 times LD. We know the extent of depletion width, which is twice XN, and you take the ratio, and you find that the boundary layer is about 38.5% of the depletion width, right? And note that this is independent of doping. It's not that I'm calculating it for a fixed doping. It's just doping just cancel out. And VBI is a very weak function of dope. I mean this thing here, very weak function of doping here. So now that you know that if I look at this, the boundary layer here is 3 times Debye length, and we are finding that boundary layer divided by depletion width is 38.5%. Is this a good approximation? 38.5%, close to 40%. Can I neglect this? It seems that the validity of depletion approximation is questionable. With 40% of this region here, and we are neglecting this particular region here, it seems that depletion approximation would be a fairly poor approximation, right? But now let me show you the results. I'll show you the results based on depletion approximation. What are the results that we are interested in? For example, what is the electric field in the junction? What is the capacitance, right? Let me show you some simulation results now. Okay. So what I want to do now is compare depletion approximation with the accurate result here. And so we have done an analysis where we find that the boundary layer is a significant fraction of space charge region here, 40% or so, close to 40%, right? So let me show you some simulation results. So what I'm doing is the following. There are a couple of simulators available. Unfortunately, demo versions are not available. They're all, you have to buy the licenses here. There's one simulator called Atlas, which allows you to, you can, for example, in this case, I created this particular device here. There's a P plus region for making good contact. And then there's a P region here. And then there's N. And then N plus, and then you have a contact. So you can create a device like this with a doping of 5 times 10 power 16 in P, and symmetrical junction with a doping of 5 times 10 power 16 in N region also. Note, it's a very thick PN junction. This thickness is 50 micron, and this is also 50 micron. Very, very thick PN junction here, and with some mobility values and all that. So I can simulate this particular PN junction, and in this case, no depletion approximation or anything is being made. The semiconductor equations are exactly solved, numerically solved. Okay, so let me show you. For example, this is how my PN junction looks. It's a 2-dimensional simulator here. This is where my junction is. And once you simulate this particular device, what you can do is, for example, you can draw a cut line like this here, and you can get, when you draw a cut line, you can get all the values. You can get hole density, electron density, energy band diagrams, anything that you want, the simulator will give it to you. Okay. For example, once I take this PN junction, I simulate it and I draw a cut line here. Cut line means I take this cross section here and I look at what happens along this particular line here. So in this case, when I draw a cut line, it says, well, you have a doping acceptor concentration till here. Red one is acceptor and green one is donor here. And we have an abrupt junction here. Acceptor goes here. And then after that, acceptor concentration is 0. I have donor and then donor concentration goes to 0 here. All right. So it just shows that PN junction here. It gives me the energy band diagram. It shows me conduction band and it shows me valence band, shows me Fermi energy. It gives you all of those things here. All right. We are interested in charge, right? So this is my space charge region and it shows me a charge like this here, which we know this is what happens. This is the, note that it's slightly plotted in an odd way. This is negative here and this is positive here. So it shows that this is the P-type region here. Charge is negative due to acceptor, and this is the N-type, charge is positive here. Okay. So both sides, since we have a symmetrical junction, both sides are the same. Let's focus on this particular region. Okay. So let me come back here. So now these are, I'm not making any approximations. These are exact results, right? So this is the charge on the N side here. As we expect, charge is constant. Starting from the junction, charge is constant, and then we get transition region here. Right? We get transition region here. What is the extent of transition region? Well, let me take a 90% point and we take a 10% point. 90% point is at 70 nanometer from the junction. Okay, 70 nanometer. 10% point is 130 nanometer. And therefore, the extent of the boundary layer or the transition region is 130 minus 70, which is 60, right? Transition region is 60 nanometer. And Debye length using a formula we calculate is 18.3 nanometer. And so 60 nanometer is about 3.3 times LD, which we said roughly the transition region would be around 3 times the Debye length here. All right, so which is what we find 3.3. So what do we see here? That the constant region, which is from here to here, roughly the constant region, which is 70 nanometer, and the transition region, which is from here to here, is 60 nanometer. Both are roughly the same. And now we are saying in depletion region approximation, we consider everything as constant. We don't consider, charge decaying like this here. All right, so let me now show you the results. So this is how charge goes. So in depletion approximation, then, are we neglecting all this charge? Think about what depletion approximation is. This is how your actual charge goes, right? Depletion approximation, what do? We approximate it by a constant region here. Does it mean that we neglect all this charge here in depletion approximation? Are we neglecting all this charge? Well, how much is this charge? Well, I can calculate, since I have the charge density, I can integrate this particular part. I find that the charge in this particular region versus the charge in this particular region is 38%. Charge in this region divided by charge in this region here. 38% of this particular. Does depletion approximation involve neglecting all this charge? If it involves neglecting all this charge, what will I expect? I'll expect huge errors, right? I'll expect huge errors. Why? Because note that what you do what do you do with the space charge region here? Well, you calculate electric field, you calculate capacitance, you calculate all of those things. How do you obtain all of those things? Well, you have this Poisson's equation written, for example, in terms of field. What you do is you need to integrate, right? You need to integrate Poisson's equation. For example, if I want to find out field, I'll integrate both left-hand side and right-hand side. So I'm integrating charge. Now, if I'm integrating charge from here and going up to here. If depletion approximation involves neglecting all this charge here, the electric field is at this junction is a result of integral of all this charge here. So the electric field would be in error by roughly the same amount, 38% or so, right? Let's see, this is the electric field that my simulator predicts here, exact analysis. It predicts a value of, here it predicts a certain value here, which we can read. Depletion approximation tells me 7.75 into 10 power 4. If I compare the maximum electric field here, determine using exact analysis versus the value given by depletion approximation, I find the error is only 4.4%. What is going on? We said that depletion approximation assumes constant charge, right? Constant charge here. And we sort of think that maybe depletion approximation involves neglecting all this charge here, right? The transition layer we are not even considering. And charge here is about 38% of the charge here. So I would expect, and we have to integrate charge to determine electric field. So I would expect a huge error, but the error I get is 4.4%. Depletion approximation seems to be working very well. The exact analysis gives me an electric field, a certain value here, and depletion approximation gives me the same electric field within 4.4% error. It's working very well. All right. Let me look at capacitance. This is how my simulator, Silvaco, is giving me capacitance as a function of bias. Let me look at zero capacitance at zero bias here, equilibrium. So I get a certain value. From depletion approximation, I get a certain value here. How much is the error? 4%. So depletion approximation seems to be working very well, giving me 4% error, right? Even though it involves a gross approximation of the charge here, right? So you have all this boundary layer here, which is so significant. There's so much charge in this particular boundary layer here. I seem to be neglecting all of that in the depletion approximation, but it's working very well. It's giving me only 4% error. So what is going on? How come it's working so well? In the maximum electric field that I calculate is very accurate. Junction capacitance I calculate is very accurate. So how come the approximation is working very well? All right. Well, the approximation is working very well in a very interesting way. All right. Let me plot the following here. So this is what depletion approximation is. The actual space charge region is. Right. And I can calculate depletion approximation W using the expression that I have. And then W by 2 would be this side here. Depletion approximation is this. Can you see what is happening? Why depletion approximation is working so well? W is not here. Depletion approximation doesn't say that W is here. When you calculate W comes out to be till here. What is happening now? Well, what is depletion approximation doing in this region? In this region, overestimating charge, right? In one region. And what is it doing here? Underestimating. And what are you getting now? See, everything that you get from Poisson's equation, you get by integrating. You get by integrating charge, right? I have to integrate once to get del psi by del x. Then I have to integrate once more and all that. So it all involves integral of charge. And when you integrate, it underestimates charge here and it overestimates charge here. And what do you get? You get a mutual cancellation of errors. The errors cancel each other. The underestimation of charge here versus the overestimation of charge here, the two cancel each other. To cancel each other, and therefore we end up getting fairly accurate results here. All right. So there are two common mistakes that people make. One is when we look at this charge in this particular manner, we think that depletion approximation is referring only to this one here. No. Depletion approximation is not neglecting the transition region here. Depletion approximation is only saying, well, my space charge region is constant. That's it. What the extent of the space charge region is, then it calculates the extent of the space charge region depending on boundary conditions. Boundary condition is that I have a net voltage of built-in voltage across this thing, and based on that, it calculates W here. And then it overestimates here and underestimates here. Let me show you some more results, interesting results here. So it works very well then. Look at a case where I've applied 0.6 volt forward bias. To my PN junction, I applied 0.6 volt forward bias, right? And look at what the charge looks like. These are from simulator. It shows how the charge in the space charge region looks like here, right? Can you see it? You can't see a constant region at all, right? There's no constant region at all here. There's no constant region here. The charge is going like this here, and the charge is going like this. What has happened? Because you're forward bias, in forward bias, what happens? The depletion width reduces here. Now, as the depletion width reduces here, what has happened is, if you go back here, that this constant region that you see here has become negligible. And then all that you're left with is this transition region here at 0.6 volt, right? All that you're left with, this is transition region here, and you hardly see a constant region here. Now, we would expect depletion approximation if we were keeping our old view of what depletion approximation is, we would have said, well, it will completely break down, right? But depletion approximation still gives you reasonable results here, okay? In fact, the electric field that I calculate using exact analysis and the electric field that I calculate using my depletion approximation, the errors are only 19%. The errors are large now because I don't even have a constant region here. The overestimation and underestimation don't cancel each other exactly. The errors are larger than this, but still 20% is pretty good, keeping in mind that it hardly looks like a constant. There's no constant region at all, right? And even in this case, what is happening is, if I take my charge here and I take my depletion approximation and I superimpose them, you can again see depletion approximation says, well, this is the region here. Again, there's an overestimation, there's an underestimation, and again, because of cancellation of errors, I end up getting results which are reasonable. Although the space charge region looks, there's no constant region at all in the space charge region. The space charge region is totally made up of, is varying charge here. But depletion approximation is saying constant, right? So it's saying constant, but still the errors are not large. The errors are still manageable, all because of this overestimation and underestimation. They cancel each other. Okay. So summary is, when we started off by looking at our depletion approximation, we said it's wrong to think of depletion approximation is not saying that space charge region is only till here. Depletion approximation is not saying that. And also it's wrong to think the depletion approximation is valid only if my depletion width is much, much larger than the transition region length here. So conventional view, if you read textbooks and all that, they will all tell you that, well, depletion region is valid because depletion width is much larger than the boundary layer. We saw that it's not true. Depletion layer width is not significantly larger than the boundary layer here. The reason why it works very well is because of this mutual cancellation of errors. Okay. All right. So that's the reason here why depletion approximation works so well. All right. This is something that I would like you to do as part of, so we showed, for example, this mutual cancellation of errors by going towards a numerical analysis. So we had a exact charge density profile from numerical analysis, and then we superimposed the results from depletion approximation, and then we calculate this, and we showed that they're the same here. What I want you to do is use an analytical approach to show why depletion approximation works so well. And so the idea is as follows. The idea is, we know that my space charge region is not constant. There's no constant charge. So what I want you to do is the following. As part of homework, assume that the space charge consists of a constant region and it consists of a transition region here. Take this particular profile. Okay, and a constant region and a transition region here, with some constant region equal to x0 and some transition region which is equal to LT. Right? So we know that space charge region has a constant region and a transition region. And the transition region is more complicated, but we have simplified it and said, suppose it's constant and then linearly decreasing from this constant to this one here, linearly decreasing over what region? Over some length L, LT. And then this is a constant region. And this is depletion approximation. So now what we want you to do is solve Poisson's equation for this case. Now you can solve it, right? Because it's a constant region and this is a linear region here. So analytically, you can solve it easily. So you can solve Poisson's equation here. And if you solve Poisson's equation, what will you get? LT is fixed. But if you solve Poisson's equation, you'll get x0. You'll get x0, right? And we've already solved Poisson's equation where we have the depletion width here. So I want you to solve Poisson's equation for this region here, for this kind of a charge density profile, and find out what is x0 here. Okay, LT, as I said, is fixed. So find out what is x0. Now, once you do that, what would you classify as the extent of the space charge region? What do you think? Space charge goes like this. What do you think is the extent of the space charge region? Well, somebody may say x0 plus LT, right, where it goes to 0 here. Somebody, well, where it falls to 10% of its value. So it's sort of this thing here. But I'll not, so you solve it. And what I want you to show is, after you solve it, finally, let me put it here. After you solve it, so that you do it here. So what you find is the following. You find this is the original charge density profile. You will find x0, and this is equal to x0 plus LT here. And you have depletion width. What I want you to show is that half of the depletion width is x0 plus 0.5 LT. So half W by 2 is x0 plus 0.5 LT. So if you superimpose half of depletion width here, what you will see is exactly the same thing here. Because it's half, so you'll see error here, exactly, overestimation of errors here and underestimation of error here. They will exactly cancel each other. All right. So the same thing which I showed you through simulation, you can show it through a comparison of this kind of a charge density profile versus the depletion approximation. And you can show that where the depletion width lies, what the relationship of depletion width is to this kind of a charge density profile. And based on the two, you can calculate what is the electric field using this charge density profile and electric field due to depletion approximation. And you'll find the electric field, maximum electric field is the same. You calculate capacitance based on this charge density profile and a capacitance based on this charge density profile, and you can show that the capacitances are the same. All right. So in a way, what this helps you to do is that what we showed through a numerical analysis, you can show through a comparison of this charge density profile versus this charge density profile. So in a way, what we are saying is, suppose the space charge density looks like this, and we are approximating it by this one here. All right. And then analytically, you can calculate all of that, and you can see why this approximation works so well for the same reason that we have talked about here. Okay.